Hi everyone, I am Dr. Kiran Raavi, working as an assistant professor in the Department of Electronics and Communication Engineering, MLR Institute of Technology, Hyderabad, India. Today, we are going to discuss UJT, which stands for Uni-Junction Transistor. The overview of today's presentation are starting with introduction to the UJT. UJT stands for Uni-Junction Transistor. So we will discuss the basic construction of UJT and we will discuss the working principle of uni-junction transistor and followed by characteristics of UJT, and then we will discuss some advantages and disadvantages of UJT and then applications of UJT, conclude with the summary. Coming to the introduction part, UJT is a three-terminal semiconductor device. The main characteristics of UJT is when it is triggered, the emitter current increases regeneratively until it is limited by the emitter power supply. So here it is a three-terminal device, semiconductor device. So that means what are the three terminals here? So let us draw this. So to manufacture or to design a uni-junction transistor, so we use some base 2, base 1. So let us consider lightly doped N-type semiconducting bar like this, and which forms base 1 and base 2. So B1, B2 means base 1 and base 2. So to this, a heavily doped P-type material has to be diffused near to the base like this, right? So this forms a gate terminal, the terminal which is called emitter terminal. Okay, so here it is a three-terminal device, and what are the three terminals? Base 1 and base 2 and emitter terminal. Okay, the main characteristics of UJT is when it is triggered, the emitter current increases regeneratively until it is limited by the emitter power supply. Okay, so the current continuously flowing through the UJT unless you are giving external trigger voltage or supply, emitter supply. So emitter is the control parameter here, emitter terminal. So that can control the current flow through the UJT. And due to this characteristic feature, it is used in applications like switching pulse generators, sawtooth wave generators, etc. So there is a switching pulse generators. So we need some specific applications in pulse width modulation techniques, particularly in communication systems. So we used to generate a pulse switching pulse generators. So specific periodic pulses you need to generate. In such case, we can use this kind of uni-junction transistors. So I hope you understand the basic construction of this UJT. So I have already discussed here. So construction of UJT, it consists of N-type silicon semiconductor bar with electrodes on each end. What are the electrodes here? Base 2 and base 1. So to this particular N-type semiconducting bar, the terminals of these connections are base 1 and base terminals, base 2. So near to the base 2, a PN junction is formed between P-type emitter and N-type silicon bar. Okay, and this forms a PN junction. So hence the name, we justify the name uni-junction. Uni-junction, there is one junction, PN junction, but it is not diode. It is a transistor because we have three terminals, emitter, base 2, base 1. The terminal of this junction is called emitter terminal, and the device has only one PN junction, so it forms a diode because the two base leads are taken from one section of the diode. Hence, the device is also called as double base diode. So we can say that this is not a it is just like a double base diode, not a transistor. The symbol for this is emitter base 2 base 1. So why this angle? Why, what it represents? This arrow represents what? So what this indicates emitter current flowing towards base 1. Why? So let us see the working operation of UJT. Okay. So with emitter open, what happens? So we are not giving any emitter voltage, P as it is. So a potential gradient is established along the n-type silicon bar. So there is a potential difference applied because we are giving only base 2 and base 1. Across base 2 and base 1 we are giving some biasing voltage VBB. As the emitter is located close to base 2, thus major part of VBB appears between emitter and base 1, because this base voltage is mainly appear across this base 2. So the voltage V1 between emitter and B1 establishes a reverse bias on the PN junction, because this is connected to negative. So there is a reverse bias between emitter and base 1 terminals. So and the emitter current is cut off, but a small leakage current flows from base 2 to the emitter. So there is a small base current will be flowing from base 2 to emitter. Thus the device is said to be in off state. So in this case we can say your UJT is in reverse bias state or off state. So coming to the second operating mode of UJT. So here we are giving some gate voltage. When a positive voltage is applied at the emitter terminal, the PN junction will remain reverse biased till the input voltage less than V1. So this is very essential point. So when you apply some voltage, the PN junction will remain reverse biased only till input voltage is less than V1. So here there is a voltage here. So between this B1, base 1, near the base 1, voltage across the base 1, that is V1. And now as soon as the input voltage at the emitter exceeds V1, the PN junction becomes forward bias. So whenever this your input voltage, emitter voltage exceeds this voltage across base 1, then only the PN junction will become forward bias. Holes are supplied from P region 2 into N-type bar. The holes are supplied from P type region into N-type bar. See here. So you can check here. This is P and this is N-type and this is base 2. So we know this is N-type bar, base 2, base 1, and near to base 2 we have emitter terminal, P-type material. So what is the basic process happen here? Here we have given some positive voltage here, and here we are giving some positive voltage here. So due to positive voltage, so and this is also positive voltage. So the P-type material having holes are the majority charge particles, and base 2 is connected to positive. So holes are being positive and base 2 also connected to positive. So this is positive and this is positive. So what happens? Positive, so repel each other. So what happens now? Whatever the holes present in the P is attracted towards the base 1. So that's why the emitter current flows towards the base 1. So that's why the current direction is like this. This is your symbol for the. So why this arrow? So all these holes are repelled by this positive terminal at the B2. So therefore these positively charged holes from P type material will attracted towards the negative terminal which is at B1. So therefore, holes are supplied from P region into N region. These holes are repelled by positive terminal B2 attracted towards the B1 terminal. Results in the decrease of the resistance of this section of the bar. Because of this, internal voltage drop from the emitter to base 1. So there is an internal drop between emitter to base 1. Region is reduced, thus emitter current increases. So here base 1 is there. So base 1 reaches the where there is a internal voltage drop from emitter to base 1 is also reduced. So therefore the emitter current also increases. So as more holes are supplied, a condition of saturation is reached. As more holes are supplied, the condition of saturation is reached. At the point of saturation, emitter current is limited by the emitter power supply. So here the emitter current is controls. The emitter current is limited by the emitter power supply. Okay. So therefore, now the device is conducting. Now the device is conducting. Hence, we can say your UJT is in on condition. So this is the second case. When you apply emitter at positive potential, so this is the process. So this is the consequence when emitter is applied positive potential. Now evaluation circuit, equivalent circuit. If you see the equivalent circuit, so here we have a RB1 and this is base voltage, biasing voltage VBB, RB2, base 2, base 1 and this is emitter voltage. Okay. So this is PN diode. So with no voltage is applied to the UJT, the value of inter base resistance is given by, so we are not giving any emitter voltage. So ideal case. So what will be the resistance? So we can, this is the N-type, lightly doped N-type semiconducting bar can be represented as a series combination of resistors. So that resistor is given by RB1 plus RB2. Okay. And now the intrinsic standoff ratio, this is the performance parameter of UJT. So which is given by V1 by VBB. So what is VBB? So because RB1 by RB1 plus RB2. Okay. So this is this can be achieved by voltage divider concept or voltage divider network. The voltage across RB1 is given by input voltage into the voltage where we have to find the voltage across that particular resistor by total resistance. So where we want to calculate the voltage? So we want voltage across the base resistor B1, RB1. So therefore it is RB1 by RB1 plus RB2 into VBB. VBB is the supplied voltage and that can also be written as eta VBB. So here eta is the intrinsic standoff ratio. The value of eta generally lies between 0.51 and 0.82. The peak point voltage of the UJT is given by Vp is equals to eta VBB plus VDD. So what is VDD here? Diode voltage, 0.7 cut-in voltage, and VBB is the supplied voltage. Right. So in this way you can calculate the peak voltage through the UJT. So coming to the characteristics of the UJT. The curve between emitter voltage and emitter current of UJT at given value of VBB is known as emitter characteristics of UJT. So on x-axis we take IE, on y-axis you take VE. So usually in context with the normal VI characteristics of normal diodes, so there we take on x-axis voltage, on y-axis current. So in contrast to this, in UJT characteristics, VI characteristics, we take current, emitter current on x-axis and emitter voltage on y-axis. Okay. So based on the voltage variations, the current also changes. At first in the cutoff region. So cutoff region means we are not giving any emitter voltage. When the emitter voltage increases from 0, due to the minority charge carriers, a small current flows through the terminal B2 to emitter. So B2 means top, on top. So I am writing here. So this is B2 and this is B1 and this is P type material. This is emitter. Right. So at first the cutoff region, in the cutoff region, when emitter voltage increases from 0 due to minority charge carrier, a small current flows from B2 to emitter. So from this to from this minority charge carriers, right? So that requires some reverse current. So above the definite value of VE, the emitter current IE starts to flow and increases until the peak. So up to peak value the current flows and it is reaches at a point P. After point P, if you increase, an increase in VE causes sudden increase in the IE with a corresponding decrease in the VE. This is negative resistance region of the curve. As with the increase in IE, VE decreases. What is negative resistance? As VE increases, current decreases here. So this is negative resistance. As per Ohm's law, V is equals to IR, right? So as voltage increases, current also increases. But here, as voltage increases, current are decreasing. So that is negative resistance region, and the negative resistance region of the curve ends at a valley point. So the negative resistance region, that is voltage increases, current decreases. This is up to certain point, that is voltage called valley point, having valley point voltage VV and current IV corresponding. So valley voltage and corresponding current is valley current. After the valley point, the device is driven to saturation. So you can observe here. So during reverse bias, so there is a leakage current. This is the leakage current, this part. So after that, so we have applied some emitter voltage and anode to cathode some positive voltage. So forward bias takes place. So from this forward bias, so there is a linear increase in the current corresponding to the voltage. So voltage increases, current here voltage increases and current also slightly increases. So after that, so it reaches saturation point, peak value. So peak voltage it reaches. So that means after that current is increasing. Voltage drop is there. So voltage drop is there. So therefore, but current slowly, what happened? Current increases, voltage decreases. See here, voltage is decreasing and it reaches value point like this. But current increases here. So you can observe from the graph. And this region is called negative resistance region. And after that value point, so it will reach some saturation point. If you further increase voltage or if you further increase this emitter current, so again after this there is a linear relation between input voltage and current. So that is, hence it is from this, after saturation it acts like a normal p-n junction diode characteristics, forward bias characteristics. So these are the VI characteristics of unijunction transistor. So coming to the applications of unijunction transistor, so they are used in particularly oscillator circuits and trigger circuits in order to initialize a specific in a circuit. Sawtooth generator. So for a specific application in pulse modulation, so sometimes you require a sawtooth waveform generation. And then what is sawtooth waveform means? So there is a slight difference between triangular waveform and sawtooth waveform. So I can write here. So this is, we can say this is your triangular waveform. So there is a exactly 90 degrees between this. Okay, this is your triangular waveform. And what is coming to this this one, this is your sawtooth waveform. This is sawtooth waveform. Okay, so for specific applications, so we have to generate a sawtooth waveforms. and bistable networks. So there are states. So what is quasi-stable state are there? So quasi-stable state means the system cannot be stay in a particular state, either on or off. So actually state means stable state. Stable state means what? If the particular circuit is in on state, then we can say it is in stable state. So if a circuit is in off state, we can say it is a stable state. But quasi-stable state means no circuit will present particularly in particular state, either on state or off state. So it is switching from on to off. So for a specific application, timer circuits, so we require this bistable networks, and in these bistable networks we use UJT as one of the leading component, and pulse and voltage sensing circuits, pulse generator, pulse circuits. Just now we have discussed. So different pulse circuits required, pulse generations required, and then voltage sensing circuits. So what kind of voltage coming as an input to the circuit. So in such case also we have to use this unijunction transistor, and then UJT relaxation oscillator, because we know the current is increasing regeneratively without giving, because the voltage drop increases at the base 1. So as base 1 the voltage drop increases means, so what happened? The resistance decreases. So resistance decreases means the current increases. So the current increases regeneratively, and so we can utilize this for oscillation purpose. So UJT relaxation oscillator, hence it is called unijunction, is also called as relaxation oscillator. And over voltage detectors, so they are used in over voltage detectors. So we can control the output current by using this UJT. So we can detect if there are any over voltages are there, so we can detect and control the over voltages. So these are the few applications of unijunction transistors. So that's all for today's session. We have discussed introduction to the unijunction transistor, and we have discussed the construction of unijunction transistor. So which consists of base 1, base 2. A simple and lightly doped n-type material has to be considered, and on either side nearby, on one side near to the base 2, we have to diffuse a p-type material. So that forms emitter terminal. So 3 terminal means emitter, base 2, base 1, right? And we have seen the different working principle of unijunction transistor, and we have discussed the characteristics of unijunction transistor, and we have also discussed the applications of unijunction transistors, right? So this is the final presentation. That means we have discussed the final concept of your 5th unit. This concludes our course of EDC subject. Thank you very much.